So since we have digital devices, there's only two levels allowed, as we said, low and high, or 0 and 1. And the various way we can combine those zeros and 1 is described by Boolean Algebra, named after Boole, who described it a long time ago. And so there's three fundamental operations you can do with the elements 0 and 1. You can take the AND of two elements, which we illustrate, also use a multiplication sign for. We can take the OR of the two, in which case we use a plus, or we can take NOT, which we either use a bar over the top of the whole expression, or a prime sometimes. And then we can talk about a function where we have A, B, and C. Each of A, B, and C can be 0 or 1, and depending on what they are, we get a different output, also a 0 or 1, which we call f. F is the function. And all the information of this function can be contained in a truth table. So, for instance, of the one input functions, there are 4 possible, right? 2 inputs, 2 outputs, of which 2 are trivial. They always give the same output. They either put out 0 independent of the input or 1 independent of the input. And the other 2 are the buffer, which just takes its input and copies it to the output, and the NOT, which takes a 0 and turns it to a 1, and a 1 and turns it to a 0. And so all the information of the NOT function can be written down in this truth table, where I have inputs here and then the output for every set of inputs. Now, there are 16 possible 2-input functions. Of which 14 are non-trivial, right, because they can still put out 0 or 1, but the other 14 are non-trivial. And I'll just illustrate here AND and OR. So an AND requires both of the inputs to be 1, in which case it's a 1. So that's this line of the truth table. A is 1, B is 1, those are the 2 inputs, and the output is 1. Notice all the other combinations give you 0. So you can say A and B in order for F. OR, on the other hand, requires either A or B, or both, to be true in order for the output to be true. By the way, when I say true, I mean the input is 1. True and false are also ways of saying 0 and 1 in Boolean algebra. So here we have a 1 output if either or both of the inputs are 0, and we only have a 0 output when both inputs are 0. And then there's other combinations. We can take NOT of both those, NOR and NAND. We can take the exclusive OR, the NOT of the exclusive OR, and then there's some others. So we can also do algebra with Boolean algebra. We can just write it out algebraically is what I mean. And so you start with a certain set of axioms. So here's my axioms, 0 and 0. Well, if 2 things are false, you still don't get a true. So 0 times 0, or 0 and 0, is 0. When you're doing AND, you need both of the inputs to be 0. So 0 and 1, or 1 and 0, is 0. And 1 and 1 is 1. Likewise, if you're taking OR, 0 or 0 is 0. This is what we saw in the truth table before. 0 or 1 is 1. 1 or 1 is 1. Also, you have to know what NOT is. NOT 0 is 1, and NOT 1 is 0. So this says not false is true, not true is false. Now, if those are just using the elements. Now, if we use variables, so it doesn't matter what A is. If you AND it with 0, you get 0. That's because AND requires both to be true. Whereas if you AND it with 1, you get A back, because you need to have a 1 here for it to be true, and if A is 1, then you get the output. A ANDed with itself is the same as itself. That's because it's either both zeros or both ones, in which case you get A. Same A or A is A for the same reason. Now, if you OR with 0, with false, you don't do anything. You still get A. If you OR with 1, well, here's your true, so you get a true output. And if you take true and not true, true or not true, excuse me, that will be true because you don't care about this and you get the true. Well, whichever one of them is true. A and not A will always give you false because if one is true, the other one's guaranteed to be false, and they both need to be true. Boolean algebra has basic properties that some of which you're familiar with. It's commutative for both ors and ands, so both addition and multiplication. Be careful, multiplication is and, so I might confuse that. It's associative. Doesn't matter in what order you do the properties of oring or anding, as long as you're doing that. It's distributive like you might expect for anding. In other words, you can and over or, so this expands to AB and BC. The tricky thing is it's also distributive of or over and. So here I have A or B and C. So I can take A or B and A or C, and that is a true thing. If I state it that way, it's perhaps a little less confusing. A or B and C is the same as A or B and A or C. Finally, there's two important theorems called De Morgan's theorems, which say that if you take the not of an and, so A and B, but not that, that's the same as saying not A or not B. And likewise, if you have A or B and you take the not of that, that's the same as saying not A and not B. You can see that from the truth tables. When you had A and B, there's only a 1 in the last spot, but that's, if you turn all the zeros to 1, that's sort of like an or, but flipped over. Here are three useful identities, and I'll prove each of them algebraically. And so the first identity says that A or A and B is the same as A. And so I'll show that. So here I have A times 1 or A times B, and I can factor the A out. So here's the A and the 1 or B. And now 1 or B is 1 by axiom. It doesn't matter what B is if I OR it with 1. So that's A and 1, which is just A. So then I finally get A or A and B is just A. Second useful identity, the identity is down here. A or not A and B equals A or B. And so I'll prove that. A or not A and B. I'm going to replace A with this identity. And so I plug that in there. And now I just use associative to recombine. And now I have A or A and B or not A and B. And now I factor out the A and not A. I factor out the B, in fact, to that side. And now I have A or not A, which I know is 1. So I replace it with a 1, and so I have A or B, proving the identity. Finally, I want to prove that A ORed with A and B, A ANDed with A or B gives A. So here I just multiply it out, AA and AD, AA or AB. A and A is just A, and A or AB is also A, and so then I've proved that identity. Another way to prove identities is to just write out the whole truth table. So I want to prove that you can distribute OR over and so I want to prove that this A or B and C is the same as A or B and B or C. And so I have A, B, and C. I have only 8 possibilities to work out, and I just go through that work. So first of all, I want B and C and A or B and A or C. So that's these columns B or C. So here B or C 0, B and C 0, 0, 0, 1. Doesn't matter what A is, so I just will repeat this on the second level, 0, 0, 0, 1. Now A or B, so if there's anything in either of those columns, there's going to be something here, and so 1, 1, 1, 1, 1, 1, 1. So here I put it, 1s, here are 0s. A or C, likewise if it's this column or that column, so here's a 1 there. Here's a 1, but it doesn't matter, 2 zeros. Here's a 1, here's a 1, here's a 1, here's a 1. So the bottom half of this all has 1s, and the top half with the C's. Notice, by the way, when I did my truth table, I always lay it out this way. I make my numbers to be ascending in binary. So this represents binary code for 0, 1, 2. It has 1, 2, and no 1s. 3, because it's 2 plus 1. 4, because it's 4 plus 2 plus no 2s plus no 1s. And likewise up to 7. So 0 to 7 represents the 8 possibilities. Okay, so finally with these 3 I can take A or B and C, so 0, 0, 0, 0, 0, 0, 0, 1, oh, sorry, 0, 1, 1, 1, 0, 1, 1, and then of course the A's all fill in down there. And the second one, I need to take the AND of these two columns, so 0, 0, 0, then 1, 1, 1, 1, 1. And so I see those, and now I compare these, and I see that they are identical, so these two functions must be the same. We should note that you can make absolutely any function using just a NOR gate, a set of NOR gates, as many as you need, but just having one type of NOR gates. You can also do it with NAND gates, but let me show. So algebraically, a NOR looks like this, right? So I have something here, I OR them, and then I take the NOT of the whole thing. So using algebra, you can say, well, what's not A? I don't have a NOT, I just have a NOR. Well, A or A is A, and then I take NOT of that. So my NOR with the inputs the same is not A. That's illustrated here, actually. So I take A, I put it into both sides of my OR, which is, of course, true, and then I turn it over so it's not true, and I get A bar. I can also combine A or 0, gives A, and then I take the NOT of that. That's shown here. I take 0, I show it as a ground, but it's a 0, and the other side I put A, and so I get NOT. A and B, by De Morgan's theorem, is just, well, if I take not A and B, that's the same as not A or B, and so I just have to take the NOT of that. And so 2 NOTs clears that up, and here's the NOT there, and that is shown here. So it's, oh, actually that's shown here. So this is not A, not B, and then I take the NOR of them to get AB. A or B is a combination of, well, that's double NOR. So here's the NOR, and then I take the NOT of that, and so I just have to figure, you know, here I had a NOT, so I combine that NOR with a 0, and that's shown here, right? So this is NOR of A and B here, and then I NOR that with 0 to get A or B coming out. The truth table itself is also a complete, as we have seen, a complete definition of a Boolean function. And in fact, we can translate between the truth table and an algebraic form as long as we do it like this. So each line here corresponds to a term. So if A is a 0, we put A bar. If B is a 0, we put B bar. If C is a 1, we put C. And so the first line, the way I always write it, will always be not A, and not B, and not C. And so each line, set of inputs, corresponds to a term with A, B, and C each appearing once, either knotted or not. And then some of the outputs are true and some are false. So we can write this as 1 times not A and not B and not C, 0 times not A and not B and C, and likewise 0 for the third row, 1 for the fourth row, which is not A and B and C, and likewise fifth row, not the sixth row, yes, the seventh row, not the eighth row. And then clearly things that are 0 we don't need to keep, we just keep the terms with 1, and so we can write this function as not A, not B, and not C, or not A and B and C, or A and not B and not C, or A and B and not C. We call this, this canonical form, a sum of mini-terms. Of course, we can, instead of taking a sum of mini-terms the way we did before, we can change all the ands into ors and take the not of everything, and so we get a different canonical form in that case, in which case we can represent a line like this, which has a 0 output. Doesn't matter. Every line we can represent, rather than saying not A and B and not C, we can say A or not B or C and take the not of the whole thing, and so that's written here, and then take the product of the rows with 0 in that form, which is shown here. So every one of these rows can either go into the sum of mini-terms or product of max terms to form the canonical form of a truth table. But you can only do one or the other, not both.